We will turn now to some general findings about absorption processes. Electromagnetic radiation can induce transitions between energy levels. For example, energy from the electromagnetic wave can be absorbed, which takes the system to a state with higher energy. But the system is selective. Only radiation with a particular wavelength can induce the transition and can therefore be absorbed. To understand this selectivity, we have to move from the wave picture for electromagnetic radiation to the particle picture. The figure shows the energy gap between the energy levels E0 and E1. A transition can occur when the energy of the photon matches the energy gap delta E between these energy levels. Delta E equals h nu. This is known as the Bohr frequency rule and applies to all spectroscopic experiments in which the photon is absorbed. The Bohr frequency rule, delta E equals h nu, is a consequence of the corpuscular theory of light. Light with low frequency, or long wavelength, can only excite low energy transitions, no matter how high the intensity is. Remember that intensity is related to the number of photons. Apart from the Bohr frequency rule, other rules exist that are specific for the particular transitions induced in the experiment. We will encounter them when we discuss transitions between particular energy levels. These rules are called selection rules, and they classify transitions into allowed and forbidden transitions. However, these categories are not absolute. In practice, an allowed transition is one which has a high probability, a forbidden transition is one with a low probability. Why then does theory predict a transition to be forbidden if it can occur in the real world, although with low probability? The reason is a deficiency of the theory applied to derive the selection rules. The theory often is based on a simplified system, which is only an approximation of the real system. We have seen above that the gaps between energy levels can be very large or very small depending on the energy subsystem. For example, the energy gaps are large for electronic states, but are very small for different electron spin orientations or different nuclear spin orientations. The gaps can be overcome by absorbing a photon with an energy that matches an energy gap. Thus, photons with low energy are needed to induce transitions between close energy levels, while photons with large energy are needed for transitions between distant energy levels. As the energy gaps in the different subsystems are very different, photons of different energies are needed to induce transitions in the different energy subsystems, or, in other words, to probe different properties of the system. Electromagnetic radiation can induce transitions from the ground state to an excited state. However, it can induce also a transition from an excited state back to the ground state. This is called stimulated emission. The total number of absorption and emission processes is given by the transition probability times the number of molecules in the initial state, which is the state before the transition. The transition probability is the same for absorption and emission when the same excited state is involved in both cases. When nearly all molecules are in the ground state, as shown on the left-hand side, there are more absorption than emission processes. Then energy is absorbed by the molecules from the electromagnetic radiation. If, however, the number of molecules in an excited state is the same as in the ground state, as shown here, then the number of absorption and emission processes is the same, and there is no net absorption of energy. The population difference between ground and excited state depends on the energy gap according to the Boltzmann distribution, as discussed before. However, it may change also during a spectroscopic experiment. At the beginning, most molecules are in the ground state. Electromagnetic radiation induces then mostly transitions to the excited state, and energy is absorbed by the system. If the intensity is high, which means many photons per time, more and more molecules adopt the excited state. When the populations of excited and ground state are equal, then there is no net absorption of energy anymore. This phenomenon is called saturation. In the following, we will introduce a quantity that describes how much light is absorbed by a sample. For this, let us consider a simple absorption experiment. The incident light has intensity I0 at wavelength lambda. It traverses a sample with a path length d. The light that is not absorbed by the sample emerges with intensity I1. We define a quantity that describes the attenuation of light by the sample. This quantity A is called absorbance or sometimes optical density. A is defined as the negative common logarithm of the fraction of the incident light that leaves the sample. I0 is the incident light intensity and I1 the light intensity that leaves the sample. Since the fraction I0 divided by I1 is smaller than 1, the logarithm of this fraction is negative. In order to get a positive value, the logarithm is multiplied with -1. Note that the relationship between absorbance and intensity ratio is logarithmic. A equals 2 means that only 1% of the incoming light transmits the sample and reaches the detector. When A equals 3, the transmitted light intensity is tenfold less. This means that only 0.1% of the incoming intensity reaches the detector. Somewhere here is the limit for accurate measurements. Higher absorbance value mean that even less light reaches the detector, which makes accurate measurements difficult. Absorbance is a quantity that does not have a unit because the intensity units cancel when the ratio is formed. Some spectroscopy programs label the vertical axis of a spectrum with absorbance in arbitrary units. This is nonsense. Absorbance has no units, not even arbitrary ones. Note that the term absorption denotes the physical process, whereas absorbance is the quantity that describes how much light is absorbed. One can say both absorption spectrum and absorbance spectrum, but not the absorption is 0.5. Correct is the absorbance is 0.5. Neither is it correct to say absorbance is a process which attenuates the incoming light. Correct is absorption is a process which attenuates the incoming light. Not surprisingly, the amount of absorbed energy depends on the number of absorbing molecules, which means on their concentration. The relationship is given by the well-known Beer-Lambert law. I am sure that you have already encountered it during your studies, and therefore I will not derive it here. The derivation can be found in any physical chemistry book, and the main steps are shown here in the middle of the slide. The law was partly discovered by Pierre Bouguer in 1729, which was cited by Johann Heinrich Lambert in 1760, and completed with the concentration dependency by August Beer in 1852. Therefore it is known also as Beer's law, Lambert-Beer law, or Beer-Lambert-Bouguer law. Absorbance which is wavelength dependent, as indicated by lambda in the brackets, depends linearly on the concentration of the absorbing molecule C, on the optical path length d, and on the molar absorption coefficient epsilon. The absorption coefficient is wavelength dependent and the property of the sample. Epsilon was previously called extinction coefficient, and this term is still widely used. However, extinction includes any light loss, also the light loss due to scattering, which we are not interested in this context. So the term absorption coefficient is more precise. Often, only the absorption coefficient epsilon max at the wavelength of maximal absorption lambda max is of interest. It is used, for example, to determine the concentration of biomolecules. The value epsilon max for electronic transitions of typical chromophores varies over a wide range from as little as 1 per molar and per centimeter to more than 10 to the 5 per molar and per centimeter. Epsilon max depends also on the molecular energy subsystem. For example, the absorption coefficient for vibrational transitions is typically a factor of 100 to 1000 lower than that of electronic transitions. When the sample concentration is very high, much light is absorbed and little light reaches the detector. This makes measurements less reliable, as discussed above. Equally difficult are measurements at very low concentrations. When only very little light is absorbed, the small difference of light intensity with and without sample is difficult to measure. Therefore, the absorption of single molecules cannot be measured. In typical experiments, the concentrations are in the micromolar range.